is still unexplored. Here's something that'll mess with your head. In 2012, filmmaker James Cameron became only the third person ever to reach the deepest point on Earth, a place called Challenger Deep, nearly 7 miles beneath the surface of the Pacific Ocean.
7 miles down, where the pressure is so intense it could crush a nuclear submarine like an empty beer can, where it's colder than your freezer, where no light has penetrated for hundreds of millions of years. And here's the wild part. That same year, NASA successfully landed the Curiosity rover on Mars after a 350 million mile journey through space. Let that sink in. We can put robots on other planets. We can photograph black holes. We can detect gravitational waves from colliding galaxies billions of light years away. But right here, on our own planet, covering more than 70% of Earth's surface, we've explored less than 5% of the ocean. 5%. Every time you look at the ocean, you're staring at a mystery that makes space exploration look easy by comparison. We know more about the surface of Mars than we do about our own ocean floor. And what we have found down there? It's stranger than science fiction. The scale of what we're missing. Earth is called the blue planet, and that's not poetic language. That's just math. About 71% of Earth's surface is ocean, roughly 139 million square miles. But it's not just the area, it's the volume. The ocean contains 99% of Earth's living space. Think about that. We live on continents in a thin layer of air. We've built cities, farms, and roads across maybe 30% of land. But the ocean? The average depth is over 12,000 feet, more than 2 miles. And the deepest point, Challenger Deep in the Mariana Trench, drops nearly 7 miles straight down. If you dropped Mount Everest into the trench, its peak would still be more than a mile underwater. So when scientists say we've explored only 5% of the ocean, what does that actually mean? It means direct observation, humans, cameras, or sensors physically present, seeing it, sampling it, understanding what lives there. Yes, we've mapped about 20 to 25% of the sea floor using sonar, but that's like saying you've explored a city by flying over it at night with your eyes closed and listening to echoes. You might know something's there. You have no idea what it's like inside. 12 people have walked on the moon. Only 3 have reached Challenger Deep. Scientists estimate there may be up to 2 million species living in the ocean. We've identified about 250,000. That means well over 1 million species could be swimming, crawling, or drifting in the dark right now. And we don't even know they exist. Why the ocean is harder than space. Here's the brutal truth about ocean exploration. The ocean doesn't want you there, and it will kill you in multiple ways if you make a single mistake.
QuickBooks Online really helps us manage both parts of the business so we can separate the cafe and restaurant and those revenue streams on the QuickBooks Online platform and really get a full overview.
Pressure. Pressure increases by 1 atmosphere
for every 33 feet you descend. At sea level, you're under 1 atmosphere, about 14.7 pounds per square inch. At 1,000 feet, around 30 atmospheres. At 6,000 feet, 180 atmospheres. At the bottom of the Mariana Trench, over 1,000 atmospheres. That's more than 16,000 pounds per square inch. Researchers sometimes send styrofoam cups down as demonstrations. They come back crushed into thimble-sized chunks. To survive that pressure, submersibles use thick titanium spheres and dome-shaped windows that cost tens of thousands of dollars each. And even then, there's always risk. One crack, one failed seal, instant death. Darkness. Sunlight doesn't go far in the ocean. In clear water, it penetrates maybe 650 feet. Below that, light fades fast. By about 3,300 feet, there is zero sunlight, and it's been dark down there for millions of years. Entire ecosystems have evolved without ever seeing the sun. When humans descend, we bring powerful lights, but those lights don't belong there. They scare animals away or draw them in unnaturally. We're not observing nature as it is. We're disturbing it just by showing up. Cold and isolation. The deep ocean hovers just above freezing, 32 to 37 degrees Fahrenheit. No seasons, no warmth, just constant cold. And communication? Radio waves don't travel through seawater. GPS doesn't work. Satellite signals don't work. Everything relies on slow, unreliable sound waves. Imagine exploring an alien world where every message has a multi-second delay. That's the deep ocean. Cost and failure. A deep-sea submersible can cost $30 to $50 million. Each expedition requires a research ship costing tens of thousands per day, engineers, pilots, and scientists, months of planning. And after all that, the mission can fail because a single O-ring degraded. NASA gets about $25 billion a year. Ocean exploration? Roughly $150 million. We spend more on one Mars mission than on ocean exploration in a decade. What we found anyway. And yet, we went. In 1960, Jacques Piccard and Don Walsh descended to Challenger Deep in the bathyscaphe Trieste. After nearly 5 hours, they reached the bottom. Do you know what they saw? A fish. A living fish, calmly swimming where life wasn't supposed to exist. That moment changed everything. Then, in 1977, scientists in the submersible Alvin made a discovery that rewrote biology textbooks. Hydrothermal vents. Cracks in the sea floor blasting superheated, chemical-rich water into the ocean. Around them were entire ecosystems, giant tube worms, blind crabs, bacteria that feed on chemicals instead of sunlight. Until then, every known ecosystem depended on the sun. These didn't. They ran on chemosynthesis. That discovery didn't just change ocean science, it changed how we think about the origin of life. Many scientists now believe life on Earth may have begun at hydrothermal vents. And if life can exist there, it could exist beneath the icy oceans of Europa or Enceladus. The deep ocean isn't just alien, it's a training ground for finding alien life. Since then, every expedition has found the impossible. Fish with transparent heads, bioluminescent creatures that glow in total darkness, jellyfish the size of trucks, animals that survive pressure we thought was lethal. Every canyon explored, every seamount surveyed, every camera dropped. Something new. So why are we still at 5%? It's not technology, it's priorities, funding and culture. There was a space race. There was never an ocean race. No flags to plant, no global competition, no dramatic launch countdowns. Space is sexy. The ocean is invisible. Rocket launches get millions of views. 3-month ocean expeditions barely make the news. We've culturally decided space is the final frontier. Statistically, the ocean is the first. Economics. There's more money in exploiting the ocean than understanding it. Commercial fishing, oil and gas, deep-sea mining. Exploration mostly gets funded when it serves another purpose. Pure curiosity? That's treated like a luxury. Why this matters now? The ocean isn't just interesting. It's Earth's life support system. It produces over half the oxygen you breathe thanks to microscopic phytoplankton. It regulates climate by moving heat around the planet. It absorbs about 1/4 of human CO2 emissions, slowing climate change, but at a cost we don't fully understand. 3 billion people rely on it for food, and it may hold medical breakthroughs we haven't even discovered yet. We've already developed cancer treatments and powerful painkillers from marine organisms, yet we've studied less than 1% of them. At the same time, deep-sea mining is accelerating. We're preparing to extract resources from ecosystems we barely know exist. The opportunity. For the first time, we actually have the tools. Autonomous underwater robots, environmental DNA sampling, AI-assisted discovery, long-term seafloor monitoring. Projects like Seabed 2030 aim to map the entire ocean floor within this decade. The next 10 to 20 years could reveal more about the ocean than all of human history combined. But only if we choose to look. The biggest mystery on Earth isn't in space, it's right here, covering most of our planet, producing the air we breathe, regulating the climate we depend on, holding life we've never imagined. 95% unexplored. Not because we can't, but because we haven't yet. If this changed how you see the ocean, hit subscribe. Stay curious.
There's a place on Earth where the pressure could crush you instantly. Pitch black, 7 miles down. In 1960, 2 men went there. What they saw changed everything. A fish, alive, where nothing should exist. Since then, we've walked on the moon, sent robots to Mars. But our own ocean? We've explored less than 5%. Creatures we've never seen. Mountains bigger than Everest. It produces half the oxygen you breathe. We still have no idea what's down there. video drops tomorrow. Let me say this very clearly. Plastic is inside your body right now. Not metaphorically, not eventually, not maybe. Right now. Inside your blood, inside your lungs, inside your brain. And this is not a theory. In 2024, heart surgeons in Europe cut open human arteries and found plastic fused into the artery walls. Not floating, not loose, embedded. They studied 257 living patients. More than half had plastic particles inside their arteries. Then they followed these people for 3 years. The patients with plastic in their arteries were 4.5 times more likely to die. 4.5. Let that number hit you. This isn't an environmental issue anymore. This isn't about oceans or turtles. This is a medical emergency hiding in plain sight. And the most disturbing part? You didn't choose this. You were never warned. You were never asked. You were never given consent. Today we're going to uncover how plastic entered the human body, why doctors are alarmed, what this could mean for your future, and what you can still do starting today. Stay with me, because the next 40 minutes may permanently change how you live. Doctors found plastic inside human arteries, and it increased death risk 4.5 times. Watch the full video. This affects you. To understand how plastic ended up inside our bodies, we have to rewind time. For 99.9% of human history, plastic did not exist. Food was stored in glass or clay. Clothes were cotton, wool, or silk. Water touched stone, metal, or wood. Then came the 1950s. Plastic was a miracle. Cheap, light, unbreakable. And that was the problem. Plastic doesn't disappear. It breaks. A bottle doesn't vanish. It fractures into microplastics. Then nanoplastics, so small they're invisible. So small they pass through filters. So small they pass through cells. For decades, scientists believed plastic stayed outside the body. They were wrong. In 2022, microplastics were found in human blood, in lungs, in breast milk, in placentas, in livers, in brain tissue. The blood-brain barrier failed. The placental barrier failed. The human body, evolved over millions of years, was not designed for this. Plastic didn't just surround us, it entered us.
We have got to the point where literally anybody can build a fully working app without knowing how to code. This is based.
The ocean absorbs our mistake. Every year, scientists estimate that more than 11 million metric tons of plastic enter the ocean. But here's what most people misunderstand. The ocean doesn't just collect plastic, it processes it. Sunlight breaks chemical bonds. Waves grind surfaces down. Salt accelerates fragmentation. Plastic doesn't remain whole. It becomes dust. Invisible fragments drift through the water column like snow. Plankton, the foundation of the marine food web, mistake microplastics for food. They ingest them. Small fish,
eat plankton. Medium fish eat small fish. Large predators eat everything beneath them. Plastic doesn't dilute, it concentrates. This process is called bioaccumulation. By the time plastic reaches tuna, salmon, or shellfish, it's no longer just passing through. It's embedded in tissue. Researchers have now identified microplastics in fish gills, fish livers, fish muscle. That means seafood doesn't only contain protein and omega-3s. It contains the chemical history of our pollution. And when humans eat fish, the chain does not end. It continues inside us. Plastic enters your body in 3 primary ways. 1. You eat it. Microplastics have been detected in seafood, salt, rice, fruits and vegetables grown in contaminated soil. Plastic particles settle into soil from the air. Plants absorb them through their roots. Food packaging adds another layer. When food is heated in plastic containers, plastic shedding increases dramatically. That microwave-safe label? It does not mean plastic-free. It means the container won't melt. 2. You drink it. Microplastics are now found in bottled water, tap water, groundwater, rainwater. In some bottled water samples, researchers found hundreds of thousands of plastic particles per liter. In many cases, plastic particles outnumber minerals. 3. You breathe it. Indoor air contains plastic fibers shed from synthetic clothing, carpets, upholstery, curtains. Every breath carries microscopic threads, and once plastic enters the body, it does not stay where it lands. Plastic has been found in blood, lungs, placenta, and brain. Share this. People deserve to know. Now here's where this stops being abstract science. Dr. Tracy Woodruff is one of the world's leading environmental health scientists at UCSF. She teaches others how to avoid toxic exposure. When she became pregnant, she followed every rule. No plastic containers, filtered water, fresh food, natural fabrics. After birth, she donated her placenta for research. The results stunned her. Her placenta contained 12 different plastic chemicals, from food packaging, from synthetic clothing, from air pollution, from tire dust. Plastic inside the organ that kept her baby alive. She later said, "That was the moment I realized this problem is far bigger than personal choice. And this is the real conflict. Plastic exposure is unavoidable. You breathe it, you eat it, you drink it. Indoor air contains plastic fibers. Water contains plastic particles. Heat releases plastic into food. Babies are now born pre-contaminated."
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But getting in the zone and staying.
And here's the most dangerous part. Plastic production exploded after 1950, meaning the first fully exposed generation is only now aging. We don't know what happens after 60 or 70 years. We are living inside a global experiment, and the data is still coming in. Now we reach the most difficult question. Does plastic cause cancer? Here is the scientifically honest answer. Plastic itself is not a radioactive toxin, but plastic is a chemical carrier. Microplastics act like sponges, absorbing and transporting BPA phthalates, PFAS, heavy metals. Many of these chemicals are classified as endocrine disruptors, carcinogenic or potentially carcinogenic, immune system disruptors. Cancer does not appear overnight. It emerges when cells are subjected to chronic stress. Animal studies show increased tumor risk when microplastics are present. Human epidemiological data is still developing, and that is the danger. We are the first generation to experience lifetime exposure. A scientist found plastic inside her own placenta. Watch the full story. Here's where the story turns and gives hope. Instead of asking, "Can we avoid plastic entirely?" scientists asked, "Can we reduce exposure enough to matter?" Dr. Woodruff ran a controlled experiment. 2 groups, same city, same air, same water. One group changed nothing. One group made simple daily changes for 30 days. No extremes, no perfection. After 30 days, plastic exposure markers dropped by 73%. Measured, verified, repeated. Later, during another pregnancy, Dr. Woodruff followed these habits again. Her placenta showed over 60% less plastic. Same woman, same environment, different outcome. This proved something critical. Plastic exposure is not binary. Reduction works. Small changes compound. Plastic exposure dropped 73% in just 30 days. Save this. As awareness grew, pressure followed. Parents demanded answers. Consumers changed habits. Governments began discussing regulation. And the plastic industry reacted. Plastic companies spend hundreds of millions of dollars lobbying against restrictions. Not because plastic is safe, but because plastic is profitable. This is no longer just science. It's a battle between public health and corporate convenience. The side that wins depends on awareness. Why plastic companies fight regulation. Share this truth. Here's the truth. You don't need to panic. You don't need to be perfect. But you cannot be ignorant anymore. Every plastic container you stop heating, every filter you install, every choice you change, it matters. Because demand shapes markets. Markets shape policy. Policy shapes the future. One day, history books will say, plastic was found inside every human body. And future generations will ask, what did they do when they found out? Now you know. Comment one habit you'll change this week. Share this with someone you care about. Subscribe for stories that actually matter.
They're gonna love my resume. But I gotta find the right word. Not
You are in a titanium sphere the size of a small car. Outside, the pressure is 20 atmospheres. That means every square inch of your submersible is being crushed with 294 pounds per square inch of force. Your skull would collapse in 0.3 seconds. You descended past 200 meters 4 minutes ago. That was the moment you left the photic zone, the last place sunlight penetrates. You are now in the twilight zone, the mesopelagic, the place where the rules change. And then you see it. A dragonfish, 20 centimeters long, needle teeth, eyes like beads. And it is the blackest thing you have ever seen. Not metaphorically black, not dark, black. It absorbs 99.956% of visible light. The submersible's 20,000 lumen floods hit its skin and vanish. No reflection, no scatter, just consumption. You thought you understood darkness. You were wrong. Darkness down here has architecture. By the time you reach 200 meters, the laws of surface biology have been rewritten. By 1,000 meters, they've been deleted. By 6,000 meters, what survives shouldn't be called life. It should be called defiance. Let's start with the first impossible thing. The dragonfish sees in red light. Red light does not exist past 5 meters underwater. Water absorbs light based on wavelength. Red, the longest visible wavelength, is absorbed first. By the time you're 10 meters down, red is completely gone. Not dim, gone. The photons have been converted to heat. The dragonfish lives at 1,500 meters. There is no red light. There has never been red light in its entire evolutionary history. And yet, it produces red bioluminescence. And it can see red bioluminescence. Human eyes have 3 types of cone cells: red sensitive, green sensitive, blue sensitive. We see the wavelengths we evolved to see, the wavelengths that exist in our environment. The dragonfish did not evolve red sensitive photoreceptors. It stole them. Dragonfish larvae live near the ocean's surface. They feed on copepods and other zooplankton that have consumed phytoplankton.
Morning. Looks like Sportselect's been around since 1990. I'm since 1990. That's weird.
In those copepods are chlorophyll derivatives, breakdown products of the photosynthetic machinery from the algae they ate. Most fish excrete these compounds as waste. Dragonfish sequester them, transport them to the retina, and repurpose them as light-detecting molecules. It's not direct theft. It's metabolic salvage across 3 trophic levels. The same molecular family plants use to capture sunlight, the dragonfish uses to hunt in a color that doesn't exist. And here's the violation that breaks intuition. The dragonfish does 2 things no other deep-sea predator does. 1. Produces red bioluminescence. 2. Can detect red bioluminescence. Most deep-sea creatures evolved to see blue and green, the wavelengths bioluminescence produces. The dragonfish created a private channel. It hunts using a flashlight its prey cannot see. This is not adaptation. This is innovation. And it is just the beginning. 200 meters, stolen vision. 500 meters, private wavelengths. 1,000 meters, entering the midnight zone. We've seen how they perceive. Now we examine how they disappear. The dragonfish is not the only black thing down here. There are at least 16 species of ultra-black fish. Different families, different evolutionary lineages. But all of them converged on the same solution. Be invisible to bioluminescence. Normal fish skin reflects about 4% of light, enough to create a faint silhouette if a bioluminescent predator passes by. Ultra-black fish skin reflects 0.044% of light. The secret is in the architecture. Their skin contains structures called melanosomes, organelles packed with melanin pigment. But it's not the pigment that makes them black. It's the geometry. The melanosomes are shaped and spaced to create a labyrinth. Light enters. It bounces between pigment structures. Each bounce absorbs a little more energy. The light never escapes. We invented Vantablack in 2014 for stealth technology and telescope baffles. Fish invented it 200 million years ago. And here's the cost. If you are invisible to predators, you are also invisible to mates. Ultra-black fish solve this with bioluminescent patterns, tiny glowing photophores on their bodies. The only parts of them that exist visually are the lights they choose to turn on. They communicate in constellations. The vampire squid lives in one of the most hostile zones in the ocean, the oxygen minimum zone. Between 600 and 1,200 meters, oxygen concentration drops to 3% of surface levels. Humans black out at 10% oxygen. Most fish suffocate at 15%. The vampire squid thrives at 3%. And if you cut one open, it bleeds blue. Surface organisms, including humans, use hemoglobin to transport oxygen. Hemoglobin is iron-based. It turns red when oxygenated. The vampire squid uses hemocyanin, copper-based. It turns blue
when oxygenated. In warm, oxygen-rich water, hemoglobin is more efficient. In cold, low-oxygen water, copper wins. Hemocyanin binds oxygen up to 3 times more efficiently than hemoglobin in the vampire squid's environment. The cost? Hemocyanin requires more energy to produce. The vampire squid's metabolism is slow, patient. It drifts motionless for hours, waiting for prey to stumble into its arms. It does not hunt. It intercepts. Every night, the largest migration on Earth occurs. You cannot see it from the surface, but instruments can. Lanternfish. Billions of them, rising from the safety of the midnight zone to feed in surface waters. Every single night, they ascend 1,000 meters. Every single morning, they descend 1,000 meters. For a human-sized organism, this would be equivalent to climbing and descending Mount Everest daily for your entire life. The energy cost is brutal. Vertical migration consumes 20 to 40% of the lanternfish's daily caloric intake, just for the commute. So why do it? Surface equals food. Depth equals survival. At the surface during daylight, visual predators, tuna, marlin, seabirds, can see you. Predation risk extreme. At 1,000 meters, there is no sunlight. Visual hunting is nearly impossible. Predation risk minimal. If this equation tilts even slightly, if food decreases, or migration cost increases, or predators adapt, the species collapses. Lanternfish are proof the equation balances. We've documented the tools. Now we examine the cost. This is the abyssal zone, 4,000 to 6,000 meters deep. The average depth of the world's oceans is 3,688 meters. This is where most of the ocean exists, and it is almost completely empty. Deep-sea organisms did not choose the abyss. They were pushed here. 252 million years ago, the Permian extinction, the worst extinction event in Earth's history, killed 96% of all marine species. Shallow seas became toxic. Volcanic gases turned oceans acidic. Oxygen vanished. The survivors were refugees. They fled to the deep, where pressure was immense, where food was scarce, where light did not exist. And they stayed. For 250 million years, they evolved in isolation, adapting to conditions so extreme they might as well be on another planet. In the deepest trenches, the Hadal Zone, evolution runs separate experiments. Trenches are isolated from each other. A fish in the Mariana Trench cannot reach the Tonga Trench. They are separated by abyssal plains as impassable as deserts. Each trench is its own evolutionary petri dish. The abyss is a filter. Every 1,000 meters removes 90% of life. What reaches the bottom is not the strongest. It is the most desperate. The Greenland shark lives longer than any vertebrate on Earth.
Radiocarbon dating of eye lens proteins, which form at birth and are never replaced, reveals ages of at least 272 years, with some individuals estimated at 400+ years. But even the conservative estimates make them the longest-lived vertebrates on Earth. And the upper estimates? If accurate, some sharks alive today were born before the scientific revolution. Their heart rate is approximately 6 beats per minute. They grow 1 centimeter per year. They do not reach sexual maturity until approximately age 150. The water they live in is just above freezing, minus 1.5 degrees Celsius. At that temperature, biochemical reactions slow exponentially. Metabolic rate is temperature dependent. Cold water equals slow metabolism. Slow metabolism equals slow growth. Slow growth equals delayed maturity. Delayed maturity equals extended lifespan. The trade-off is absolute. Speed and heat equals death. Stillness and cold equals time. So much time you outlive empires. In 2019, during a routine bathymetric survey of the Challenger Deep, instruments recorded something unexpected.
You, just you, building your app on base 44.
Movement below 8,000 meters, below where most fish can exist. The contact lasted 11 minutes, moving at approximately 0.4 meters per second, then vanished. It was filed as unidentified biological contact. No follow-up expedition has relocated it, but the data remains. For decades, scientists believed life could theoretically exist at any ocean depth. Pressure was a challenge, not a ceiling. In 2024, that assumption shattered. The Mariana snailfish holds the record for deepest living fish, found at 8,178 meters in the Mariana Trench. When researchers analyzed its tissue, they found extreme concentrations of a molecule called TMAO, trimethylamine N-oxide. At extreme pressure, proteins, the molecular machines that run all life, begin to collapse. The pressure disrupts the bonds holding their shape. When proteins lose their shape, they lose their function. When they lose their function, the organism dies. TMAO acts as a chemical anchor. It stabilizes proteins under crushing pressure. Surface fish, approximately 50 millimolar TMAO. 1,000-meter fish, approximately 150 millimolar. Mariana snailfish, approximately 300 millimolar, the highest concentration ever measured. Here's the breakthrough. Scientists calculated the maximum pressure TMAO can counteract. The answer: approximately 8,400 meters depth. An entire planet's worth of ocean where fish cannot exist. Below 8,400 meters, even maxed out TMAO cannot save proteins. For fish, the ceiling is absolute. But fish are not the only form of life. Single-celled organisms, bacteria, archaea, have been found at full ocean depth, 10,994 meters. They survive using entirely different strategies. No complex organs, no nervous system. Just chemical gradients and membrane pumps. The 8,400-meter limit applies to multicellular animal life. What exists below that line is no longer anything we would recognize as an animal. In 2024, researchers published something disturbing. Amphipods collected from the deepest ocean trenches, depths exceeding 10,000 meters, contain microplastic concentrations higher than surface fish. Trenches act as gravity funnels. Microplastics have near-neutral buoyancy. They don't sink quickly. But over months and years, biofouling, algae and bacteria colonizing the plastic surface, adds weight. Eventually, they sink. And because trenches are topographic low points, currents concentrate debris there. Once plastic reaches the Hadal zone, it cannot leave. No upwelling, no predators migrating upward to redistribute it. The deepest places on Earth are one-way garbage chutes, and the contamination is permanent. We polluted the Hadal zone before we finished mapping it. The abyss was supposed to be untouched. It was supposed to be the last refuge. We've mapped what exists,